Hello, and welcome to Astronomy 100. In our last segment, we talked about how we were able to see how Isaac Newton was able to determine the behavior of light, how it travels from one place to another, by doing a brief experiment in a laboratory in his home. He was able to take light, pass it through a prism, turn it into a rainbow, and then turn that rainbow back into white light. Now, the important thing to remember is that the light that enters the prism is what we call white light. And let's go back to our picture here so we can see what we were talking about. When light enters the prism, it comes in as what we call white light. But the fact that we call it white light has some pretty important consequences. And that's where I'd like to begin in this particular segment. The term white light is an important term when it comes to the physics of light. And the definition of white light is the presence and mixture of all of the colors of the rainbow. So an example is here on the screen. We have a rainbow that shows the red through violet colors. And if you recall, red, orange, yellow, green, blue, violet are the official colors of the rainbow. But this definition of white light is an important one because what it means is that if a source of light is what we call white light, it has every single one of those colors present. So if, for instance, the light has red, orange, but no yellow, and then includes green, blue, and violet, in other words, missing the yellow, it is not technically white light. So it must have the presence of every single one of the Roy G. Biv colors of the visible spectrum. The other part of the definition is that all of these colors are mixed together. So when you take all of these component colors and you mix them into one source of light, it is what we call white light. Now, it sounds trivial. It sounds as if the words white light simply mean light that is white, but it is not necessarily the case. So keep in mind this definition, and I'm going to show you two examples of how this definition of white light can be a little bit confusing if you stray from the definition itself. So let's start with the first idea. The concept of white light is one where light sometimes will have this definition satisfied, but will not actually look white when you see it. And the example I have here on the screen is, this is a photograph taken of the element on the top of an electric stove. If you were to turn the stove all the way to the high position, and what you'll notice is that the stove has this orangish, reddish appearance to it once it becomes heated up fully. This person just dimmed the lights in the room and took a photograph. And so what you can see in this picture is the color coming from this heated element that's on the top of the stove does not look white. If anything, you would say it has an orange color to it, maybe a reddish orange color to it. But this light coming from this heated piece of metal is actually white light. If you were to take the light from this hot piece of metal, pass it through a prism, and look at the rainbow that comes from this piece of metal, you will actually see all of the colors of the rainbow, red, orange, yellow, green, blue, violet, all of them are there. And so the presence and the mixture of all the colors together means that this source of light satisfies the definition of white light. But notice, it does not look white in appearance. So sometimes white light is not necessarily white in appearance. Now here's sort of the opposite. Sometimes there are sources of light that look white in appearance, but they do not meet the definition of white light. And the example I'll give you is a very standard type of what we call a compact fluorescent light bulb. These are those light bulbs that you commonly see in your everyday life that are more and more these days replacing old incandescent light bulbs. Now, when you turn on this light bulb, you'll notice that it has a very white appearance to it. However, if you were to take the light from this light bulb, pass it through a prism, you will not see every single color. In other words, some of the colors of the rainbow are missing from this source of light, but yet in the right mixture, having the right combination of colors can give you the perception of white. So this is an example of a source of light that looks white but does not meet the definition of white light. So it's very important that you understand in the material that we're going to continue to go through, that when it's referred to as a source of light being white light, that it is the presence of all the red, orange, yellow, green, blue, violet colors mixed together into one particular mixture or quantity of light that you perceive as white. The other thing that goes with this is that there is no part of this definition that says that all colors must be equal in quantity. So you must have the presence of all of these Roy G. Biv colors, but there's no rule that says you must have an equal amount of red, as yellow, as green, and all the way to violet. So you don't have to have all of the colors in equal amounts. You just have to have them present in some certain amount. So let's go back to this picture and I'll show you what I mean by this. In this picture here, this source of light has all colors present, but they are not equal in quantity. In this heating element here, this hot piece of metal, it is a tremendous amount of red, still quite a bit of orange, a pretty good amount of yellow, but there is very little violet. Now keep in mind, violet is still coming from this piece of metal, but it's a small amount in comparison to the red, and so therefore you'll notice it has a reddish appearance even though it technically has all the colors present. So the idea that white light must have all of the colors present but not equal in quantity is an idea that we're going to come back to, and you'll find very quickly that this is something that will play into how we understand the nature of light. Now, the next thing I want to show you is, even though Isaac Newton was able to show through his experiment with a prism that light has this feature of being able to spread out into a rainbow, and then that rainbow being put back together into white light. And if you recall from that previous segment, this is a demonstration of how light behaves as a particle. Particles can be sorted out and particles can be recombined, which is what the prism is doing in that instance. Although that is true, in the year 1801, a scientist by the name of Thomas Young was able to show that light instead actually travels as a wave rather than a series of particles. So let me show you how this works. In 1801, Thomas Young, and here's his picture, came up with an experiment to prove that light actually behaves as a wave rather than a particle. Now this takes a little bit of explaining, so let me walk you through how his logic comes to this particular conclusion. Thomas Young noticed that if you have the ability to look at the seashore and look out, be on the seashore and look out to the ocean, if you live in a place where there is a seawall that prevents the ocean waves from hitting the shore directly, and this is very common, there are many marinas and harbors around the world that have an artificial seawall that is in place, and the idea is that when ocean waves come in, there's two small openings to allow you to get your boat in and out, but the waves are essentially going to hit the seawall, and thus this protects the shoreline. Now what Thomas Young noticed is that these two openings in the barrier, in the seawall, and in this particular case, this is a top-down view looking down onto the top of this. He noticed that when the waves pass through the barrier opening, that there's a behavior that the waves have that makes it very interesting, that's very different than particles. The waves come in parallel, but when the waves pass through the opening, they bend, and as they bend, they fan out. So in other words, you'll notice the shape of the wave changes to this bent shape, and then of course it gets wider and wider and fans out. If there are two openings to the barrier, what you find is that the bent waves will pass over each other and create a very complicated pattern. And we'll come back to that in just a minute. But let me start off with a picture here. This is a photograph taken in a laboratory looking down onto what we call a wave tank. This is just a shallow tank of water where there's a barrier that's been put in, but there's an opening in the barrier. Off the picture, which you can't see, there is a wave machine, essentially something that constantly pushes the water to create parallel waves that will cross the tank. And you'll notice how the waves are moving from left to right, coming in parallel. But once they encounter the opening, you can see quite easily how the waves will bend as they pass through the opening and they fan out. So this is an actual photograph of this very phenomenon. Thomas Young noticed that where there's two openings, the one set of waves will actually interact with the other set of waves and create what we call an interference zone, meaning one set of waves is interfering with the other set of waves. The result is that at various locations in this zone, you're going to get an interesting phenomenon occur. Let me show you what that is. In certain places in this zone, you'll have one set of waves with its peaks and valleys cross over another set of waves with its peaks and valleys, but you'll notice that the peaks will pass over each other. In other words, a peak passes over a peak and a valley passes over a valley. The result of this is the peaks will join together to make one larger peak, and the valleys will join together to make one deeper valley. And so the combination of these two waves creates one larger, meaning taller and deeper wave. And this is what we call constructive interference. Two waves construct one single larger wave. However, in other places inside of this interference zone, you'll have the exact opposite occur. What you will get is the peak of one wave will pass over the valley of the other wave, and vice versa, and what you end up getting is the peak of the first wave will fill in the valley of the second wave, and so therefore the wave cancels itself out. Essentially, the wave nullifies itself, and we call this destructive interference. So in this zone, you get a variation of constructive interference and destructive interference and constructive interference and so forth as you move along this interference zone. Now here's where I'm going with this. Let me first show you a recreation of this. Notice the waves coming in parallel, and then as they pass through the openings, you can see that the one set of waves fanning out crosses over the other set of waves fanning out, and what you end up getting is this weird pattern called an interference pattern. Everywhere you see it look very smooth, this is destructive interference, and everywhere you see it look like a set of waves, this is constructive. Notice you have destructive, constructive, destructive, constructive interference. So you get what's called an interference pattern as a result. Thomas Young said this can't happen with particles. And you'll notice in this instance, if we have a bunch of bullets that are coming in on the barrier here, notice where the bullets hit the barrier, they don't get through. Where they hit the opening, of course, the bullets make it through. So a bunch of particles hitting a barrier don't create this interference pattern. They just can't because they're particles. So Thomas Young did a very famous, now very famous experiment. This is called Young's double slit experiment. What he did was he passed a source of light through a single opening, then let that light pass through a barrier with two openings, and what he ends up projecting onto a screen is a pattern that looks exactly like this. This is a photograph of the interference pattern. And what you'll notice is you see bright and dark and bright and dark and bright and dark because this is that very constructive, destructive, constructive interference pattern that light will produce when it passes through the barrier. His conclusion is light must travel as a wave of energy rather than a particle of energy. So it seems as if the discovery of Thomas Young contradicts the discovery of Isaac Newton. Newton shows that light travels as a particle of energy, and Thomas Young shows that light behaves like a wave of energy. The problem is, each of these two experiments are perfectly legitimate. So it seems as if there's a contradiction here, that light can behave as a particle when you want it to, and it can behave as a wave when you want it to, and it seems like one or the other has to be correct. Turns out, they're both correct. What we now know about light is it behaves both as a wave and as a particle simultaneously. So it has what we call a wave-particle duality. And this very nature of light makes it unique among other forms of energy in our universe. Light can do something that other forms of energy can't. It has this dual nature to it. And what we're going to do is take advantage of both. We'll talk about light as a wave of energy, we'll talk about it as particles of energy, and there are things we can learn by describing it individually as a wave or as a particle, and we'll see what we can do with that. We're just about out of time, so we'll start with that next time. I hope you'll join me.